Numbers play a fundamental role in the physical sciences, particularly physics. So let's talk about how we want to write our numbers through this semester. Physics is about measurement. Measurements are done with numbers. Numbers represent physical measurements, must have units. Physics deals with significant range of numbers that vary from the size of an atom to the distance between galaxies. If you haven't watched the Powers of 10 video in Canvas, now pause this one and go watch it. It'll give you a feel for what we're talking about there. The ways that we're going to write our numbers are decimal, scientific notation, or engineering notation. Scientific notation does two things for us. We're going to talk about significant figures and how to represent them, and it makes it clearer without ambiguity what our significant figures are, and it shows the size in the exponent of the power of 10. Engineering notation is like scientific notation, only we have powers of 10, only powers of 10 that are divisible by 3, so that enables us to go, say, between kilometers to meters or milliseconds to seconds quickly and easily. Powers of 10 in scientific notation, the power of 10 tells you how to move your decimal. So example 1.2310 squared. Right away we see 3 significant figures, and 10 squared means we move that decimal. 10 to the minus 2 means it's a small number, so we move the decimal the other way. We get 0.123. Now, all measurements in the physical sciences have uncertainty. Some of it's because of the device you use to make the measurement, but even more so, it's a fundamental fact of nature that there are things that you cannot know exactly. There's limits to what you can measure. That's expressed as the Heisenberg uncertainty principle. We're going to talk primarily about errors, which are the uncertainty in the experimental measurements. If engineers are going to be making things, so the ideas are the same, but it's called tolerance, in that you have to tell me how closely accurately I need to make something. And all numbers that are calculated from a measurement have uncertainty in them. Now, the first way we control that uncertainty is with significant figures. Uncertainty in a measurement, we show the proper number of significant figures, which all of them we know to be true except the last one that has uncertainty in it. We only include one digit that has uncertainty, and all of those added up will be our number of significant digits or significant figures. I'll use those interchangeably. There's some rules on handling them. First, you need to be able to know how many there are. All non-zero digits are considered significant, so this first number has 4. This one only has 3 because that 0 is not significant. It's only a placeholder. And the same thing with this 0 here. So both of those have 3 significant figures. So there's a little bit of ambiguity there. If there's a 0 between other significant digits, it counts. So 101 has 3. 0.509 has 3. But zeros that occur between a significant digit and decimal are not. So 0.140508 only has 3, only the 508 part. 8920 only has 3. If there were 4 and the 0 was significant, then I would need to put a decimal. The advantage of scientific notation is it's easy to see both the number of significant figures without ambiguity and the size of the number. So this number, there's only 3 significant digits, and we count how far to move the decimal. We got 3, 6, 7, 8. So 1, 2, 3, 10 to the 8. Notice if it's a plus, it's a big number. 3 significant digits. Now this one is the same, 3 significant digits, and we move the decimal 1, 2, 3. Minus 3, it's a small number, so it's a negative exponent. But they both have 3 significant figures. 4.56 times 10 cubed, written as a standard number, is going to be 10 cubed is 1,000, so 4560. You can either move the decimal or you can multiply. 4, 5, 6, 10 to the minus 3 is going to give you a small number, so you're going to either divide by 1,000 or move the decimal 3 the other way, and you get 0.00456. Again, both have 3 significant figures. How many? Both have 3. When dropping digits which are not significant, then we're going to round. And the standard way to do that if the first digit dropped is 5 or greater, then round it up. If it's not, then leave it alone. Addition and subtraction. Don't carry the result past the first column containing a doubtful digit. So, for example, if these are measured values, and I'm going to add them up, I'm going to do your addition, and you can see that's uncertain, so that'll be uncertain, so that's the uncertain, so we need to drop all the others, and that's a 7, so we need to round it to a 2. Here, right, now those are not significant, so we've only got 3, so when we add it up, that's the last one we want to keep, and so that's a 1, so we're going to leave that a 7. That makes sense, right? If one's uncertain and you add it to the one that is certain, it's uncertain. So we only keep. Ambiguous case is like this one. The number of significant digits could be. So again, in scientific notation, if there were 3, in scientific notation, we'd get 3.50. E to the 4th is the same as 10 to the 4th. That's calculator notation. And so we would have 3 significant figures. But we couldn't tell that here. Some people used to write a little line over it sometimes. Multiplication and division, the idea is you keep the number of digits that the smallest one has. So here's an example. Suppose I need to square 234. Then if I square it, I'll get that. And if I round it to 3, I would get that. Justification for uncertainty is plus or minus 0.5. Here's an example. So suppose it's uncertain by half. So suppose it were 234.5 and you squared it. 234.5 and you square it. You can see you get different numbers. If we round them, that's my doubtful digit. So you can see that's the first one that's different. So that's the doubtful digit, and notice it's 1, 2, 3. So the rule is, however, if you're multiplying or dividing 2 numbers, you keep the number of digits in the answer as the smallest one in the ones you're using to multiply or divide. If no other information is available, then textbooks usually work with 3 significant figures. So on homework problems, if you're not clear, then pick 3. Okay, now there's going to be a little quiz over that material, and we're going to have a little measurement exercise that will help us practice our significant figures. If you have any questions, shoot me an email.